In our last film, we looked at the restoration of the stone floor. Today, we're concentrating on the mechanical side of the restoration, in particular the Wentworth beam engine and the Hurst frame. The work is being carried out by a group of volunteers, the Beeleigh Mill Restoration Group. The current millwright, James Alden, explained why they are important to the project.
Now, Essex County Council is the only council, as far as we know, in England that actually has a bespoke millwright. That's myself, of course. But there's only one of me, and I've got several mills to look after, and I can't be at every one all of the time. So we encourage groups of friends from the local community to come into our mills and help open them to the public, and if they're capable, help us with any restoration work that we feel that we can get on with. In particular, in the case of Beeleigh, we have a very good group of people who were formerly engineers and so forth, mostly retired, who are willing to put their own time in to help us out with our restoration work.
Oh yeah, look, it's now.
Beeleigh Mill was originally built as a water mill in the 10th century, with this steam plant added in 1845 so that milling could continue in times of drought or low tide. Sadly, the catastrophic fire of 1875 destroyed much of the water mill, and now only parts of the brickwork remain. But miraculously, the building that housed the steam engine survived, as did the Hurst frame, elephant boiler and the Wentworth steam engine. Steam had been used in Cornish mines since the early part of the 18th century, so by the time the Beeleigh Mill steam engine was developed, engineers like Newcomen, Watt and Hornblower had all played a part in improving the basic design. Within 4 years of Boulton and Watt's patent expiring, Arthur Wolff patented his design for the two-cylinder compound engine, and it's this design that's the blueprint for the steam engine installed here in the mill at Beeleigh. So let's meet some of the team responsible for getting this wonderful example of Victorian engineering repaired after lying dormant for nearly 150 years. Rob, what was the condition of the engine like when you first came here?
Remarkably good, considering it was installed in 1845. But following the fire in the water mill next door in 1875, the engine room was just shut up and they just left it. We suspect that because the fire was in February, that the engine was not being used over the winter when there's flow in the river, because the price of coal would be expensive, and therefore it'd be uneconomic if you've got plenty of water. The cylinder bores, when we've taken the cylinder covers off, was almost nowhere at all. We were expecting a step at the top of the cylinder bore where the piston ring stops moving and starts to go down again. Nothing there. It's absolutely as machined originally. The piston rods themselves have been remachined, but they are the original ones. But they were just skimmed up because where they were exposed and where the gland was bearing on them, they'd become pitted. But we suspect that because the fire was in February, the engine had been greased and left for the winter. And pretty much most of it is as you see.
Presumably, though, it wouldn't turn when you wouldn't have tried to turn it.
We didn't try to turn it because we thought we would do too much damage.
Yes.
So we really had to make sure we've got the cylinder covers off, the pistons out, and the covers off the valve gear, and the regulator down here was stripped and cleaned, and the bearing covers all round were removed and checked, both in here and the bearings in the Hurst. The only bearings that do show any signs of wear are the thrust bearings on the Hurst, but they are quite likely original and replacement items anyway, because you've got quite a low bearing on it. You've got the flour in there because we've got effectively what is really a firewall between the two to make sure the sparks don't ignite the flour.
But so when you've done all of this, you were now able to turn it, and you had an electric motor to drive the thing round.
Yep.
How long did it actually take then, from that time you first came in here and looked at it, to actually getting it to rotate?
Yeah, well, I wasn't in the first wave of people coming in here. I was sort of recruited a bit later, but probably 6-7 years work for us. But it was only Tuesday afternoons.
Yes.
Apart from when we sent things away to be done, which was really, as far as I can remember, only the piston rods that were sent away. One of the other colleagues made the replacement parts for the regulator. And of the significant parts, that's the only ones that have been done. And it was remarkable, when we first ran it on compressed air, we just reassembled it, making sure we reassembled everything exactly where it was. Switch on the compressor, open the regulator, and off it went.
So what is the general description of the type
Well,
of engine?
this is rated as a 12 horsepower and 2-cylinder beam engine with the cast iron beam and the cast iron connecting rod down there, down to the crank at the bottom. Parallel motion here so that the piston rods move vertically, because if they were just attached to the end of the beam, they would move in an arc, and therefore they would move backwards and forwards.
Yes.
And that would obviously mean you couldn't seal with the gland there if it was moving significantly. And that was designed and patented by James Watt originally, and he's always said that was his best invention. And we've got 3 parallel motions. We've got the third one here going down to what they used to call the air pump, which pulls up the condensate for recycling the water.
Right.
So the steam enters from the boiler behind us into the steam jacket, and then through the regulator here and the valve chamber into the high pressure cylinder. It's used there, and then into the larger low pressure cylinder where it's used a second time, and then exhausted downwards into a condenser below where the steam is turned back into water. That creates a partial vacuum which improves the efficiency of the engine. Again, that's James Watt's invention, and again patented, so nobody else could use it until those expired. Once the water is condensed, this air pump with the third parallel motion draws the water up and recycles it back into the high pressure feed pump, which then, as necessary, pumps it back into the boiler. So that protects the boiler from corrosion products, because the water is recycled all the time, so
Right,
the
yes.
corrosion products get used up,
Yeah.
and therefore you're using purified water.
Now you mentioned earlier about the piston rings.
Yep.
Now I'm familiar with piston rings in modern internal combustion engines as being a single or several rings of metal on the piston that run
Yep.
up and down inside the cylinder. Now I get the impression from looking at this that this is somewhat more complicated than that, of being a much earlier design. Can you tell us a bit about that?
It was, and it came as a complete surprise when we drew out the first piston. There was lots of bits.
So you've got a model.
We have a
of
model.
the piston here. Yeah.
Yeah, and it's essential to show what's going on, and it's all held in place with wedges. Most of the things are held in place with wedges here, and that shows you that. So we just take this off, and this is a facsimile made by members of the team, and the piston rings are in three pieces. Those are the main piston rings there, and we have these brass wedges pushing outwards and pushed out by springs.
By that spring.
So when we took it out, all we did was clean it and reassemble and put it back.
So that is a clever design, isn't it? Because
Yeah.
that's very thick, that ring. So
Yep.
it's got able to take a lot of wear.
Yep,
What was the metal used that
Well,
was
we-
used for that?
that was, the ring itself was cast iron,
Mm-hmm.
and so again, that is still similar to car engines up until now,
Mm-hmm.
where you've got cast iron cylinder bores,
Yeah.
or a cast iron liner in aluminium, and a cast iron piston ring. Because of course in 1840s there was no mineral oil lubricants, so they'd probably be using tallow,
Right.
and those parts are missing on the engine. There's no tallow cocks on here. There should be on the other side there, one on each cylinder.
Now I'm noticing as we're standing here the bolts that hold the cylinder heads on.
Yep.
They're pretty solid, chunky bolts, those, aren't they?
They are.
Are they the threads that are on them? Is that specific to this engine, or I mean, this is pre-Whitworth, I presume.
It is pre-Whitworth, so therefore it is not standard. If you measure the diameter and then measure the pitch of the thread and then look in the tables, it's nothing like it. Fortunately, I was able to screw cut on my lathe, replace the bolts, which we can see two there,
Yes.
and we can also see that this one, we condemned it because it's got a crack got cracks in it going
Yes, I see
vertically.
those cracks.
And that was in this position here where it holds the two cylinder heads down, cylinder covers. The reason that they probably cracked like that is that they use what looks like putty to seal the cylinders. And of course, if these were not dead level, you've got a bending moment on the bolt,
Yeah.
and therefore a possibility of
And being shocked by the movement of the pistons
Yeah.
up and down. So we've been talking about those coarse threads that you've got on the cylinder head bolts there, but I'm noticing on this rod that is going along here that that's actually got some very fine threads on it.
Yeah, these are almost micrometer threads.
They are.
And the reason for that is to adjust the effective length of this bar here, which has an effect on the parallel motion.
So one of the other necessary features of a steam engine is that if you don't have any means of governing the speed, they can basically run away. They just go faster and faster and faster until they would explode.
Yep.
What's the way in which this machine is controlled so that that doesn't happen?
Well, it's even more critical than that, because obviously the miller next door wants this engine running at a constant speed.
Right.
And the speed we believe is about 30 RPM,
Mm-hmm.
which is not fast by modern standards, but when this is going at 30, it is quite interesting. So to govern the speed, initially we have the main regulator here on this handle here, and then we've got the vertical here going through this linkage mechanism down to the governor down there, where we've got these two cast iron balls. As the engine speeds up, those move out, and that adjusts the speed
Right,
there.
so that's just basically then closes off the steam source.
Closes or opens the steam source,
Whichever,
depending
yeah,
on
whichever way
whichever
it's
is
gotta go.
necessary, having roughly set it with the main control valve.
Let's now have a look at the boiler, Rob.
Yep.
It's clearly fairly rusty, as we would expect from the amount of time that it's been here. Are you hoping that we're going to get that restored at some point and ever be able to use it again as a source of steam?
No, never. We would never get a boiler inspector to pass it. We don't know what the material is exactly, and we don't know what the thicknesses are. And we do know that down below, out of sight, there is some significant corrosion. There was a report done for County in 1995 when the boiler was still in reasonable condition at that time, and they drained it down, which I think was probably the worst thing they could do. And since then it has deteriorated quite a lot. But it's just too unknown anybody to ever try to fire that again. But in principle, how it worked is you've got this big cylinder on top, and then below there are two smaller cylinders, and there are cross tubes staggered, so they're not in opposition to each other to even out the stress. I didn't even thought of that at the time. And they run most of the length back there. So you've got two small tubes, and then this big one above with interlinking tubes. And then the fire is right at the bottom, and then the flue goes round and then up, where you can see the mark there where the old
yes,
chimney
in the
has been
corner.
demolished. The steam is tapped off here,
There, yeah.
and used to go across and then down into the engine. We have the main turn-off control valve there. It's not really a regulator, it's just an on-off switch as far as we know.
Oh yes, on that square head.
On that square-headed
So
piece
you'd
there.
have a lever on there.
You put a lever or spanner on there to turn it on and off. And in front of that you've got a point for filling it initially. These
Safety valve.
two safety valves here, and in the centre there we have a level indicator. Now,
Oh, I see. So that would
that
just
goes
sort of
up and
floats
down.
Up and down
yeah, we're
and
not
these
quite
would-
sure how, and there'd be weights on the end of those
to set the pressure.
to set the pressure.
Yeah, an inspection chamber.
And then you've got an inspection chamber there. There's another safety valve at the other end.
Oh yes.
That's, we think, is the main one, it's certainly the biggest, and that vents through the wall, whereas these one would vent into here. So we think these would be secondary ones to the main one there. And then under this walkway here is the water from the high pressure pump we mentioned earlier, under there, and pumps water back in here. And that would be controlled by the engine man in here, looking at the level indicator there. The stoke hole is outside, so there'd be somebody in there shoveling coal in to keep the fire going. We think there was a sight glass out there so he can see the level, but there's nothing he can do about it anyway.
So quite obviously, Rob, so it's not ever going to produce steam. So we're not aiming to get the engine to run on steam. So how will you run the engine for future demonstrations?
We have now an electric motor down here which drives it relatively slowly.
Yes.
Probably about 5 to 7 RPM, so nowhere near the speed to run millstones.
I think you said with 30 RPM.
We need 30. We have run it on compressed air with a road compressor that used for pneumatic drills, and we can get it up to about 30 psi with that. The problem with that is that there is a potential for condensation in the compressed air.
Of course.
And we don't have any drain cocks in the cylinders.
Right.
So as a permanent solution, and this is what we're thinking of, is in the first place a compressor, but a compressor that only compresses to about 30 to 40 psi. And we're having meetings to discuss exactly our strategy on that, but we'd have to put a dryer in as well to make sure that we don't get an accumulation of condensation, and therefore we get hydraulic lock, because obviously water won't compress, and if the valve is closed and the piston comes down, there's sufficient water there, something's got to give.
And of course you've got risk of corrosion as well.
Risk of corrosion as well.
Yeah.
The plan would be that we would run it on the electric motor for half an hour afterwards to pump the air through it, fresh air through it, to hopefully disperse any condensation as well. But
okay, well, so you've got the electric motor there, and you've got a kind of a crude clutch mechanism in effect, using a rubber wheel to drive it.
Yep.
I think the best thing we can do now, Rob, is press the button and run it, don't you?
Yes, yes.
Paul, I've just been talking to Rob in the room next door. We've been talking about the steam engine. I presume that the steam engine is driving this shaft to this giant gearbox.
Yes, that's correct. The power comes from the flywheel through this shaft to the pit wheel, then to the wallower, up the shaft to the spur wheel. And what we call this, what you call a gearbox,
yes.
Is we call a Hurst in milling terms.
Well, earlier when we were on the stone floor, it was pointed out that an important aspect of the grinding is to set the gap between the stones so that you get the right grade of flour. Now what I see here looks like, is this the mechanism that you use for setting the gaps on the stones?
That's correct, yes. So when the engine's stationary, we can engage what we call the stone nut by turning this, and there's a keyway on here, so this shaft will rotate, turn the top stone, the bed stone stays still, and the gap between them is really important, and this gap can be adjusted by turning this handle. There's a threaded block in here that lifts and lowers that, so that gap can be just changed a tiny amount. And the miller will check the flour with his finger and thumb, and that's where we think rule of thumb comes from.
Right. I couldn't help but notice when you were winding that down that some of the gear teeth look like iron and some of them look like wood.
That's correct. I'll hand over to Martin, who can explain.
So Martin, I was intrigued to know why it is that some of the gear wheels are iron and some of them are wood.
Well, the most important thing is that in mills, because of the combustible nature of the air, due to the air, the flour floating around in the atmosphere, it's very combustible. So you have always wood against metal to prevent sparks from igniting. And also there's an element of the sacrificial element of when if the engine should stop suddenly, the teeth will break rather than the cast iron ones. So here you have the wallower, that's got 78 teeth on, and they are all heartwood oak in very good condition. Hardly any worm in them at all. All held in the back with tapered wedges all round. You can see it on the back edge there. Very easy to replace. You just knock the wedge out and the tooth comes out and replace them. Then we go up to the spur wheel and we've got 184 teeth up there. Most of them are in pretty good condition, and we thought after consultation that due to the small amount of work that it's going to be doing, we could just replace the very, very bad ones. A lot of them are quietly bad,
my goodness, yes.
with
Woodworm and dry rot.
Mainly the ones at the back of the Hurst where the roof disappeared, that got wet, were the rotten ones. So at the top spur wheel we have 184 applewood teeth, And I've got a fairly large stock of apple wood, so I've been gradually replacing these. And this is an example of what we have. Lots of rot, woodworm infestation. And interestingly, they're all put in with this metal gauze, probably due put in as an extra packing to make them good tight fit. And then they're held up against the cast iron spur wheel with these spikes coming in through the top and the bottom. You see
that stops them falling out.
That stops them out falling out, and you can see the indentation of the mark from the drive side of the teeth from the stone wheel.
So why apple wood? So you say that those ones are oak.
These are oak, heartwood oak.
And the ones up there are apple.
Well, we don't know. I don't really know. I've tried to look into it, but most of the books talk about apple wood for the teeth. It's very hard wood, and it's a certain amount of very fine grain, and it's a certain amount of self-lubrication. Although a lot of them would have had grease put on them, I think.
So the interesting question would be is whether they've been in there right from the start or whether they were replacement.
Yeah, no, these are all original. These are all original.
So I wonder how many bags of flour that
Yeah,
made.
incredible amount. Although we don't think it had a lot of use. It was something like 20 years, was it? And we don't think it had a lot of use because they say these are all the original teeth, all the oak teeth on the wall are original. So one would imagine that there was someone making teeth, and as they wore out, they would put new ones in.
Mm. So we've now covered some of the major elements of the restoration work involved in getting this far, most of which was covered in previous episodes. But what we haven't seen is the huge administrative tasks required to manage the work, the research, the fundraising, grant applications, open days, group visits, and much more. In our next episode, we will be looking at a working watermill so that we can follow the milling process from start to finish. So I hope you'll be able to join me when we meet again at Alderford Mill.